A temperature map of the Northern Hemisphere in the middle of August looks as though someone has drawn a sharp, invisible line across it. The coloring isn't uniform. It comes in patches. Over Western Europe, from the Pyrenees to the Alps, from the Atlantic coast of France across to the plains of the Pannonian Basin, a nearly unbroken patch of deep red spreads across the map, shading into maroon and almost black in the places where daytime highs are climbing past 40 degrees Celsius, about 104 degrees Fahrenheit. A little over 1,000 miles to the northeast, over Scandinavia and much of Eastern Europe, the colors tell an entirely different story. Pale blues and soft greens, marking temperatures below the seasonal average. Between these two worlds, separated not by an ocean, but by a distance a jet plane covers in a few hours, runs a border that shows up on no political map. And yet, it decides whether tomorrow in a given city will be unbearably hot or cool and rainy. Follow that same map for a few weeks instead of looking at a single snapshot, and a more interesting pattern appears. The red zone shifts, but at times it changes position only slowly, lingering over the same broad part of the continent instead of moving steadily eastward. Farther northeast, cooler and cloudier conditions can persist at the same time. The result is a temperature pattern that can remain surprisingly stable for days, even while individual weather systems continue to evolve within it. What makes heat linger over some regions for days, sometimes for weeks, while other regions only a short flight away sit on the opposite side of the same atmospheric system, as if shielded by something invisible? Why can a single high-pressure system stall over one place for so long that the ground cracks from dryness, rivers drop to their banks, and the grass turns brittle and yellow? And can we even talk about a single uniform summer, when at the very same hour people on one part of a continent are wilting in 40-degree heat, while people less than 2,000 kilometers away are reaching for a jacket in the evening? The answer isn't found in a single fact or a single event. It comes together out of several processes that are usually studied in isolation from one another. The circulation of air high above the ground, the behavior of clouds, the moisture locked in the soil beneath our feet, the temperature of open ocean water thousands of kilometers from the nearest coastline. Taken separately, each one sounds like a narrow, technical detail. Put them together, and they form the very mosaic we see on the map. Summer 2026 gives an unusually clear opportunity to work through that mosaic. This isn't a story about the planet simply getting hot. That framing would be too simple and not accurate. This is a story about distribution, about how the energy arriving from the sun gets redistributed among the ocean, the land, and the atmosphere, and why the outcome of that redistribution looks like a mosaic rather than a single, even wash of color. To make sense of that mosaic, start with the simplest building block, a region of high pressure that meteorologists sometimes call a blocking ridge. Picture an enormous dome of air, slowly sinking down over a particular region. As air sinks, it warms through compression, and the moisture inside it has a harder time condensing into clouds, so the sky clears and stays largely cloud-free for days on end. A clear sky means sunlight reaches the surface almost unhindered, day after day, gradually loading up the ground, the pavement, the walls of buildings with more and more energy. The absence of clouds actually cuts two ways, and it's worth pausing on that. During the day, a cloudless sky means nearly the full stream of incoming solar radiation reaches the ground without a reflective cloud layer in the way. But at night, That same clear sky lets the heat the ground absorbed during the day radiate freely back out into space, which, on its own, should produce cool nights. Except if the air trapped under that high-pressure dome happens to be humid near the surface, say because of a nearby warm sea, that nighttime cooling effect weakens considerably, and overnight lows stay high. That combination, scorching days paired with unusually warm nights, turns out to be one of the most physically demanding aspects of these stalled weather systems for the human body, because it leaves no window for recovery between one hot afternoon and the next. If a high-pressure system moved on after a day or two, the heat would have less time to build. But sometimes, the large-scale circulation evolves slowly enough that a ridge remains influential over the same broad region for an extended period. Atlantic weather systems may be diverted around it, and the usual sequence of changing air masses can be interrupted. That persistence, rather than the existence of high pressure by itself, is what allows heat and dryness to accumulate. That is essentially the picture observed over Western Europe in 2026. The first hint of an unusual summer arrived as early as May, when a persistent heat dome settled over the region and broke May temperature records in several countries. At the time, it looked like an isolated event, intense, but seemingly a one-off. It turned out to be only the first in a series. By the middle of August, Western Europe had already lived through its fifth major heat wave of the season, and at the peak of the most intense stretches, daytime highs across broad areas reached or exceeded 40 degrees Celsius. Global atmospheric models used by the American Space Agency to track surface air temperature captured this sequence of waves continuously. A running map of daily highs from the 1st of May through the 19th of August shows dark red zones appearing, briefly retreating, and then reappearing again, almost pulsing over the same stretch of the continent. To understand why an atmospheric wave can get stuck like that in the first place, it helps to bring in another piece of the system, the jet stream. This is a narrow but extraordinarily powerful ribbon of wind that blows roughly 10 kilometers up, right at the boundary where the weather we experience day to day gives way to the upper troposphere. It exists because of the temperature contrast between cold polar air and the warmer air of the mid-latitudes. And that contrast is what accelerates the airflow to speeds that can rival, and at times exceed, that of a freight train. The jet stream is rarely a straight line. It bends and loops, tracing waves not unlike the curves of a river seen from above. Under some atmospheric configurations, these large waves can become slow-moving or persistent, and the weather systems associated with them may remain over the same regions for much longer than usual. In those situations, a ridge of high pressure can dominate an area for days or longer instead of being quickly replaced by the next system. An important caveat belongs here. The science of how the jet stream's behavior is changing over time is complex, still developing, and full of open questions. Researchers are actively studying whether rapid Arctic warming may influence some aspects of mid-latitude circulation and the behavior of large atmospheric waves. But it would be inaccurate to claim that any single stretch of persistent heat is fully explained by that mechanism. The atmosphere is an extraordinarily complex system, and the jet stream's behavior in any given season is shaped by a whole range of factors at once, including conditions in the tropical oceans and the extent of the previous winter's snow cover, among many other variables. The more defensible statement is that blocked atmospheric patterns create conditions under which persistent heat becomes more likely, not that we can point to a single, certain cause behind any one episode. A useful way to picture this is as a large wave in a moving river. Some wave patterns travel onward quickly. Others change only slowly and can remain in roughly the same place for an extended period. The atmosphere can behave in a similar way. When a large-scale wave pattern becomes persistent, the ridges and troughs associated with it can keep influencing the same regions day after day. During important stretches of the summer of 2026, the circulation over the Atlantic and Europe repeatedly favored high pressure and heat in the west, while lower pressure and cooler conditions were present farther east. The exact pattern evolved with time, but the contrast between the two sides of the circulation remained one of the season's defining features. This is also why contrasting conditions can exist relatively close together. Different parts of the same large-scale circulation can favor very different weather. A ridge may support hot, dry conditions in one region, while a neighboring trough helps bring cooler air, clouds, or rain into another. The precise connection has to be evaluated for each episode, but the broader lesson is clear. The warm and cool patches on a temperature map are shaped by the structure and movement of the atmosphere, not by isolated local processes alone. While the air sits motionless over a region, another mechanism starts working at ground level, one that steadily amplifies the intensity of the heat over time. This is the feedback loop involving soil moisture. When soil holds plenty of water, a significant share of the incoming solar energy goes not into directly heating the air, but into evaporating that water, a process physicists call latent heat of evaporation. That's why a damp meadow feels noticeably cooler on a hot day than the dry asphalt right next to it. Part of the energy hitting the meadow is literally spent turning liquid water into vapor, rather than raising the temperature of the surface. But if a high-pressure system sits over a territory long enough, the soil gradually dries out. Once the moisture stored in the upper layers of ground is used up, evaporation has nothing left to draw on, and nearly all of the incoming solar energy starts going straight into heating the air and the surface instead. That sets up a reinforcing loop. Dry soil drives temperatures up more sharply, and the higher temperatures, in turn, accelerate the loss of whatever moisture remains and dry the land out further still. In the summer of 2026, the combination of prolonged heat and a lack of rainfall became especially visible in the river basins of Central Europe. Sandbars emerged along stretches of the Danube, and the falling water level began to affect not just river shipping, but power generation as well. Hungary's Paks nuclear power plant, which relies on Danube water for cooling, was forced to sharply reduce output, running through much of August at only a fraction of its normal capacity. A complete shutdown was avoided only through emergency engineering measures to keep the water level high enough at the plant's intake. Similar constraints tied to the low Danube affected energy facilities in neighboring countries as well. That detail matters. Prolonged heat and drought don't just show up as record numbers on a thermometer. They put real strain on infrastructure that depends on steady river flow and an adequate supply of cooling water. Here is a question that sounds simple, but has a complicated answer. Why doesn't one heavy rainstorm immediately erase a long drought? After a prolonged dry spell, the upper soil can become very dry, crusted, or locally water repellent, and intense rainfall may arrive faster than the ground can absorb it. Some of that water then runs off instead of reaching the root zone or deeper groundwater. The response varies with soil type, vegetation, slope, rainfall intensity, and how long the drought has lasted. So a dramatic downpour can raise streams quickly without fully restoring the water stored in the landscape. Meaningful recovery often requires repeated rainfall over time, not just one storm. Dry land carries another kind of risk as well: fire. A lack of moisture in grass, shrubs, and forest litter makes vegetation far easier to ignite, and wind can spread a fire across a much larger area very quickly. In the summer of 2026, wildfires accompanied hot, dry stretches in several parts of Europe, including France and the Balkans. It's important not to conflate the conditions with the direct trigger, though. Heat on its own doesn't set a forest alight. What heat and drought do together is prepare the fuel, drying out the vegetation and making it that much easier for a fire, once ignited, to spread. To really understand the picture of 2026, though, it isn't enough to stop at the atmosphere and the land. You have to go, quite literally, down into the ocean. Water has an enormous capacity to store heat. Raising the temperature of a kilogram of water by 1 degree takes roughly 4 times as much energy as raising the same mass of air by the same amount. That's why the ocean functions something like the planet's giant thermal battery. It absorbs surplus energy slowly, but it also releases that energy gradually, influencing the atmosphere far beyond the location where the heat was originally absorbed. According to Europe's Climate Monitoring Service, sea surface temperatures across the tropical and extratropical oceans outside the polar regions were the highest ever recorded for the month of July in 2026, based on the service's full observational record. What matters here isn't the record number by itself, but what it says about the background state of the ocean. Across parts of the Atlantic and the Mediterranean, pronounced positive temperature anomalies and marine heat waves persisted through the summer. An ocean in that state enters the second half of summer carrying a substantial reservoir of stored heat, which it then releases into the atmosphere gradually over time. A marine heat wave is a period during which sea surface temperature in a given region runs significantly and persistently above the seasonal norm. These events can directly affect marine ecosystems, everything from coral reefs to fish populations, but their significance reaches far beyond marine biology. A warmer ocean surface can support greater evaporation when the atmosphere allows it, increasing the amount of heat and moisture available near the surface. Under the right circulation, some of that influence can extend inland, but the relationship is not automatic. A warm Mediterranean does not by itself cause a particular heat wave on land. Ocean temperature changes the background state in which atmospheric systems develop. The outcome still depends on winds, humidity, pressure patterns, and the history of the air mass involved. But why should ocean temperature matter at all to someone living hundreds of miles inland, far from any coast? Because the ocean and atmosphere constantly exchange heat and moisture, and the atmosphere can transport those properties far from the coast. Air moving over an unusually warm ocean may acquire additional heat or moisture before being carried inland, although how much of that signal survives depends on the path the air takes and the weather systems it encounters. The important point is not that the ocean controls inland weather from a distance, but that it helps set part of the background from which regional weather develops. And here the film's central pattern shows up again. A high water temperature by itself doesn't determine the specific weather that follows on land, and it doesn't guarantee a particular kind of storm will develop. The ocean sets an important energy backdrop, but the outcome depends on the state of the atmosphere above it, winds at different altitudes, humidity, the position of high and low pressure systems, and the path of the large-scale atmospheric waves. That's exactly why two equally warm patches of ocean can, in the very same period, feed into two entirely different weather outcomes. The Pacific deserves a brief mention as well. Conditions across the tropical Pacific in 2026 were being watched closely as El Niño developed and forecasts assessed how the event might evolve. El Niño is associated with unusually warm surface water in the central and eastern equatorial Pacific, together with changes in the tropical atmosphere, and it can shift weather probabilities far beyond the ocean where it begins. For this story, though, it should be treated as one part of the wider background, a large-scale influence capable of redistributing heat and altering circulation, but not a complete explanation for the temperature pattern over Europe. Now return to the temperature map this film opened with, and look at it more closely. This is where, arguably, the most important turn in the whole story is hiding. Even though individual countries in Western Europe, France, Spain, the United Kingdom, set outright temperature records over the course of the summer, the overall figure for the continent as a whole didn't come out looking quite so record-breaking. The reason lies in the sharp divide between West and East. While thermometers in the western part of the continent were pushing past historical peaks, temperatures across Eastern Europe and Scandinavia in July actually ran below the climatological norm. It was the combined effect of these two opposite anomalies that produced the final picture. Western Europe lived through its warmest June-July stretch on record, with an average temperature of roughly 21.5 degrees Celsius, close to 3 degrees above normal. While for the continent as a whole, July landed among the warm months, but not an outright record, tying for second place with July 2024. That contrast isn't some statistical fluke, and it isn't a reason to doubt that real changes are underway. Quite the opposite. It illustrates the central idea of this whole film almost perfectly. Extreme heat in one region and comparatively cool weather in another can absolutely coexist, because the atmosphere isn't a flat, uniform layer. It's a system of waves, and the crests and troughs of those waves distribute heat in a deeply uneven way. That's why judging the global climate from the weather in one city, or even one country, can be deeply misleading. What looks contradictory on a local map can make sense once the view widens and the larger circulation pattern comes into focus. It's worth pausing on a question that sometimes gets raised as an objection. If part of Europe was cooler than usual this summer, doesn't that undercut talk of a warming climate overall? The answer comes down to the difference between weather and climate, two concepts that are easy to confuse but describe fundamentally different scales of time. Weather is what's happening in the atmosphere right here, right now, in a specific place on a specific day. It has always been variable, and it will always include both unusually warm and unusually cold stretches, simply because that's how the wave structure of atmospheric circulation works. Climate, on the other hand, is a statistical summary of weather, averaged over decades and across broad regions. A single cool July in Scandinavia doesn't cancel out or disprove a long-term trend, any more than one cold day in the middle of a warm week cancels the arrival of summer. Cooler weather in one part of Europe doesn't contradict the bigger picture, precisely because the two observations sit on entirely different scales, one local and immediate, the other global and measured across years. The same logic extends beyond Europe. At any given moment, the Northern Hemisphere contains regions running far above their seasonal average, others close to normal, and others below it. Humidity, elevation, soil moisture, cloud cover, and the origin of the air mass can make two places with similar daytime temperatures feel and behave very differently. The temperature mosaic is therefore not an exception that needs to be explained away. It is the normal spatial structure of weather, unfolding on top of a climate background that is measured over much longer periods. Specific observations from early August help illustrate the scale of the contrast. On the 6th of August, the Meteorological Service in Slovakia recorded 42.2 degrees Celsius, about 108 degrees Fahrenheit, in the village of Dolne Plaktince, an all-time national temperature record. And the record it replaced had lasted exactly 1 day. On the 5th of August, a different station in the country had logged 41.4 degrees. Numbers like these matter less as isolated milestones, and more as markers of how intense the air mass was and how stable the overall weather pattern had become. At the same time, high-level heat warnings were in effect across a number of countries in Central and Southern Europe, and the falling level of the Danube was becoming an increasingly visible constraint on both agriculture and energy production. At that point, the temperature map had stopped being a purely meteorological story and become a matter of everyday infrastructure. Europe wasn't the only place demonstrating how quickly a persistent ridge of high pressure can reshape a temperature map. In mid-July, satellite monitoring picked up a heat dome sitting over the western United States. Several weather stations in Montana, Wyoming, and Utah set all-time temperature records during that stretch. That episode is useful for comparison precisely because the underlying physics was similar. A persistent ridge suppressing cloud cover and convection, allowing the surface to heat more intensely, even though the geography, the duration, and the specific consequences were different. The same basic type of atmospheric configuration doesn't produce identical weather everywhere it occurs. The outcome always depends on the state of the surface underneath it, the local humidity, the terrain, and the air masses surrounding it. All of these events are better understood not as one universal mechanism at work, but as the interaction of several layers of the climate system at once. A persistent area of high pressure can trap hot, dry weather in place. A deficit of soil moisture can further amplify surface heating. An unusually warm ocean shifts the baseline for heat and moisture exchange with the atmosphere, and large-scale circulation determines exactly where these factors converge at any given moment. Under the right conditions, they can reinforce one another, but the contribution of each factor varies from region to region and from one episode to the next. That's precisely why understanding the interaction between these processes matters more than searching for a single cause behind the entire temperature map. Of course, no single season, however striking, can be attributed automatically to one single cause. Any individual weather event is the product of many interacting factors, including the natural variability the atmosphere has always had, long before the climate began shifting noticeably under the influence of human activity. Researchers who study the attribution of specific weather events use dedicated statistical methods for this purpose, comparing the likelihood of a given event under today's conditions with the likelihood of that same event in a hypothetical climate without human influence. Work like that takes time and careful analysis, and the accurate thing to say is that a particular set of background conditions, a warmer ocean, drier soil, a specific configuration of atmospheric circulation, can influence the probability and intensity of episodes like these, without claiming that any single event of the summer of 2026 was directly caused by those longer-term shifts. There's one more detail worth dwelling on, one that's easy to overlook. Not all of the heat accumulated over a summer disappears the moment a heat wave passes or a drought on land finally breaks. The heat stored by the ocean over the summer doesn't dissipate the instant autumn arrives. Water cools far more slowly than air does, precisely because of that same enormous heat capacity discussed earlier. The release of that heat back into the atmosphere is stretched out over time, and it can continue shaping weather conditions for months after the calendar has officially turned to fall. Which brings us to the last question worth asking in this film. One that isn't about the summer that has already happened, but about the autumn that's approaching. Could the heat accumulated over the summer influence how autumn begins? This calls for particular care in how the question is framed. Nothing in the currently observed conditions allows anyone to say with confidence that specific extreme events will definitely occur in the autumn of 2026. It's essential to keep observation of what has already happened clearly separate from forecasting what might happen next. These are two fundamentally different kinds of statements, and they shouldn't be blended together. That said, over the coming weeks, specialists who monitor the climate system will be watching a set of interconnected variables closely, each capable of influencing how the season unfolds. First among them is sea surface temperature, whether it holds at record levels across the Atlantic and the Mediterranean or begins to decline as autumn approaches. Then there is the evolution of El Niño in the tropical Pacific, how ocean and atmospheric indicators change as the event develops, and whether forecasts of its future strength are borne out by new observations. Soil moisture in the regions that lived through a prolonged summer drought matters just as much, whether it recovers before winter sets in, or whether the deficit carries over into the next season. Meteorologists will also be tracking the position of high-pressure systems and the behavior of jet stream waves, since those factors determine whether autumn weather systems move through at a normal pace or get stuck over the same territories again. Particular attention will go to the marine heat waves still lingering in several parts of the world's oceans, along with conditions in the Arctic and the state of sea ice. In July, Arctic sea ice extent ranked as the 6th lowest on record for that month in the satellite era, with especially thin ice cover in the northern Barents Sea near Svalbard and Franz Josef Land. Changes in the Arctic are of interest not only in their own right, but because many researchers are studying possible links between the state of the Arctic and the behavior of atmospheric circulation farther south, an area of research that remains active and far from fully resolved. No single one of these variables tells the whole story on its own, but taken together, they function something like the planet's instrument panel, letting observers track which way the balance is shifting between the energy stored up over summer and its gradual release as the season turns. If ocean surface temperatures stay elevated longer than usual, those waters can continue supplying relatively large amounts of heat, and when atmospheric conditions favor evaporation, moisture, into the lower atmosphere after the calendar has moved into autumn. If soil moisture stays depleted, regions that endured a summer drought will enter the fall season in a vulnerable state, where even ordinary dry spells can feel more severe than they would in years with a healthier water balance. And the character of large-scale circulation over the northern hemisphere will determine how quickly autumn weather systems move through. If stable, slow-moving configurations form again, particular types of weather could linger over regions longer than usual. But there's no way to determine in advance, purely from the summer's pattern, exactly where that might happen, or whether it will mean heat, cold, dryness, or heavy rain. The story of the summer of 2026, in other words, is nowhere near finished. It's still unfolding, and how it plays out will become clearer as new data comes in over the coming weeks and months. Return now to the map this film began with. In its opening minutes, it looked like nothing more than a scatter of bright patches, red where it was hot, blue where it was cooler than usual. Back then, that picture might have registered as a random pattern, almost an abstract composition with no underlying logic. By now, after everything that's been laid out, it reads very differently. A red patch no longer registers as simply heat. Behind one might be a persistent ridge of high pressure. Behind another, the transport of a hot air mass, a parched land surface, or some combination of several factors at once. The boundary between red and blue stops looking like an arbitrary line, too. It reflects the movement of air masses and the large-scale structure of the atmosphere, continually redistributing heat between regions. And underneath all of it runs a slower process, the continuing exchange of energy among an unusually warm ocean. Land surfaces whose cooling through evaporation can weaken when they dry out, and an atmosphere that connects those regions through circulation. None of the three acts alone, and none tells the whole story by itself. Perhaps the most important thing about this summer's story isn't any single temperature record, however striking it might have looked in the moment. What's far more interesting and far more revealing is watching how the distribution of heat shifts among the planet's three great reservoirs, the ocean, land, and atmosphere, and how those three components keep interacting with one another, producing the very same complex living mosaic visible on the temperature map. That map hasn't settled into something fixed. It's still changing right now, even as this film plays, and what happens to it in the months ahead will be worth watching just as closely.